Welcome back to my channel. This is Dr. Leena with the lecture series on signals and systems and Python. This is the third lecture. Let us have a recap of what we covered in lecture 2. In lecture 2, we defined the continuous time and discrete time signals with examples, and the following standard signals in continuous time domain were also studied: a unit step signal, unit ramp signal, unit impulse signal, a sinusoidal signal, and an exponential signal. In today's lecture, we shall see continuation of standard signals in continuous time domain, rectangular, triangular, exponentially decreasing, sync, and signal, and standard signals in discrete time domain, exponential signal, unit step, ramp, and impulse signals, sinusoidal, and rectangular signals. So a rectangle signal is defined as rect of t is equal to 1 for mod t less than t naught and 0 otherwise. So graphically it looks like this. So mod t less than t naught means for both negative and positive values of t naught from minus t naught to plus t naught. Within that range it will have a constant value of 1. So here this graph represents that for a particular value of t naught is equal to 5. So from minus 5 to plus 5, mod t less than 5 means minus 5 to plus 5, it will have a value is equal to 1. So this is the rectangle signal defined. A triangle signal. A triangle signal is defined as tri of t, that is equal to 1 minus of mod t, where mod t is less than t naught and it is 0 for all other values of time. So what is this 1 minus of mod t? So mod t means both positive and negative values of t. So this 1 minus of mod t represents a straight line. So we have the equation for the straight line given by y is equal to mx plus c, where m is the slope of the straight line and c is the intercept, the point at which it cuts the y-axis. So for positive values of t, that is for t greater than 0, this is of the form 1 minus of t. So here this I can write it as minus t plus 1. So this will have a slope of minus 1 and intercept of 1. So slope is minus 1 and intercept 1 for t greater than 0. For t less than 0, this becomes equal to 1 minus of minus t, that is plus t, for t less than 0. So this I can write it as t plus 1, so which is a straight line having slope is equal to 1 and intercept at 1. So the graph looks like this. So if I take t naught is equal to 1, so from minus 1 to plus 1, the signal exists from minus 1 to plus minus t naught to plus t naught. Here t naught is 1, so it exists from minus 1 to plus 1. So what is the way in which, or the fashion in which it varies between minus 1 to plus 1? For negative values of t, it is a straight line with positive slope and intercept 1. So slope is 1, that is positive. Positive slope indicates that as you vary the one of the variable, that is x, as you increase the value of x, y value also increases along this line. Then we call it as a positive slope straight line. So this is, as we increase the time from minus 1 to 0, we see that the y value increases from 0 to 1. 0 to 1, and 1 is at the intercept, the point at which it cuts the y-axis. So this is the straight line which is t plus 1 from minus 1 to 0. For positive values of t, it follows as minus t plus 1, that is it is a straight line with negative slope and intercept at 1. So negative slope means as you increase the x value, the y value decreases along this line. So as we increase the time from 0 to plus 1, the y value decreases from 1 to 0. That is what is the physical significance of negative slope. So this is a straight line with negative slope, intercept at 1. So between minus 1 to 1, these two straight lines form a triangle, and hence it is a triangular signal. So next, an exponentially damped sinusoidal signal. So an exponentially damped sinusoidal signal is given by x of t is equal to a naught e to the power of minus alpha t into sine of 2 pi ft plus phi in general. So this is a product of two signals. So it looks like this. It is sinusoidal, but amplitude decreases exponentially. So it is a product of two signals. One is the exponential signal given by a naught e to the power of minus alpha t. The other one is a sinusoidal signal given by sine of 2 pi f t plus phi, where f is the frequency, pi is the phase displacement from 0 crossing. So this first signal a naught e to the power of minus alpha t for a particular value of a naught is equal to 5 and alpha is equal to minus 2. Its variation is like this as shown in figure 2. And a sinusoidal signal with 50 Hz and phi is equal to pi by 4 is as shown in figure 3. The product of these two signals will result in a signal shown in figure 1, which is exponentially decreasing sinusoidal signal. So next is a sinc signal. A sinc signal is given by sinc of t, that is equal to sine of pi t divided by pi. This is a normalized sinc signal. So this will have a value 1 at t is equal to 0, and on either side of this y axis, the amplitude of the signal goes on decreasing, and the signal crosses the 0. It will have 0 values at t is equal to 1, t is equal to 2, t is equal to 3, like this. That is for integer values of t. It will have the 0 value on either side of this y axis. For both positive and negative values of t, for integer values, the signal crosses 0 on either side. This is the sinc signal. So next we have the signum signal. So the signum signal is defined by sine of sig of t, that is equal to, it will have a minus 1 for t less than 0 and plus 1 for t greater than 0, and its value is 0 at t is equal to 0. So this is shown here. For t negative, its value is minus 1. For t positive, its value is plus 1. At t is equal to 0, its value changes from minus 1 to plus 1, and it will have a value is equal to 0 at t is equal to 0. Next, let us take the standard discrete time signals. So one is exponential signal. So next, standard discrete time signals. The exponential signal. So it is given by x of n is equal to a into r to the power of n, where r itself is e to the power of beta. So this will take different forms depending on the value of r, whether it is positive or negative, whether it is greater than 1 or a fraction. So if r is positive, then we'll have two cases. One is for r greater than 1, the other one is for r a positive fraction. So when r is greater than 1, this r to the power of n, as n increases, it is exponentially increasing discrete time signal. So this becomes an exponentially increasing standard signal. So next comes when r is a fraction, positive fraction. Positive fraction raised to the power n, where n goes on taking integer values, it will have a decreasing values as n increases. So this is an exponentially decaying signal. Next, when r is negative. When r is negative, a into negative quantity raised to the power of n, where n takes integer values. So the x of n depends on whether n is sign of this x of n depends on whether n takes odd value or even value. So this will have a positive sign for all even values of n, and it will have a negative sign for all odd values of n. Further, if r is greater than -1, it will have a exponentially increasing signal, but alternatively we will have positive and negative values of the signal. For all even values of n, we will have positive value for the signal, and for all odd values of n, we will have the negative values of the signal. And as n increases, it is exponentially growing. Next, if r is a negative fraction, here also alternatively we will have positive and negative sign for the signal, but it is exponentially decreasing because it is a fraction raised to the power of n. So for all even values of n, we have the positive values for the x of n, and for all odd values we have the negative values. And as n increases, it is exponentially decreasing. So next we have unit step signal. Unit step signal is defined as 1 for values of n greater than or equal to 0, and 0 for n less than 0. So we should remember that n can only take integer values. So for all n positive, we have the value of the unit step signal as 1 unit step signal, and for all negative values it is 0. So this is a discrete time unit step signal of strength 1. If it is other than 1, say 2, then it will have all values 2 for t greater than 0, and this is going to be a step signal of strength. So next is ramp signal. Ramp signal is defined as r of n is equal to n for n greater than or equal to 0, and it is 0 for n less than 0. So and graphically it is represented like this. So when n is 1, its value is 1. When n is 2, its value is 2. So it is a unit ramp signal. Okay. Discrete time unit ramp signal. Suppose if it is a other than unit strength, then it will have that particular value as n increase. Say for example, it is 2 times r of n. So that is ramp signal with strength 2. So then we will have when n is equal to 1, we will have the value is equal to 2. And when n is 2, its value will be equal to 4. That is twice the value of n it will have. Then a unit impulse signal is defined as equal to 1 for n is equal to 0 and 0 for all other values of n. Only at n is equal to 0, we will have the signal of value 1 and its value is 0 for all other values of n. Discrete time sinusoidal signal is defined as x of n is equal to a into sine of omega naught n, where omega naught is the discrete frequency. So this is a sinusoidal discrete time signal whose magnitude varies sinusoidally like this. We shall see more about whether it is going to be periodic or not, how it is obtained, all those things in future. Next is a rectangular signal. A rectangular signal is defined as equal to n for mod n less than or equal to n naught. This is an example for n naught is equal to 5, that is mod n, that is from -5 to +5. It will have a value of 1, so it is a discrete time signal with value 1, and for all other values of n it is 0. That's all for today. Thank you for watching. Like, share, don't forget to subscribe. You can download the video Link is given in the description box and leave your comment in the comment box.